So let's start this next example. So we have a 8.5 liter tire filled with 0.55 moles of gas at a temperature of 306 Kelvin. So what is the pressure of the gas in the tire? And again, maybe make like mental notes about how we know that this would be compared to any of our other problems that we've done, how this one would be an ideal gas law problem. So nothing's changing here. We're just given, this tire has some amount of gas in it at a certain temperature, at a certain volume. What's the pressure? So the simple gas laws have to have a change. Ideal gas law is just going to be, these are the conditions. Calculate whatever the remaining condition is. So again, PV equals N RT. So pressure, volume, moles, and temperature are the four possible variables. And then R is a constant. So 0.0821 atmosphere liter per mole Kelvin. And I would start out every problem, if you think it might be an ideal gas law problem, just write down R with its units, because you're going to have to match those units from whatever the question gives you. So what's our pressure for this? What's the pressure in the tire? Aha, pressure is what we're looking for. So we don't know the pressure, but we want to find it. What units of pressure will we get? Tires are usually measured in North America in pounds per square inch. That's pounds per square inch. But using the ideal gas law, what are the units of pressure? What are the units of pressure in R? Atmospheres. So in R, in the ideal gas law constant, atmospheres is the pressure. That's what we'll get from this. Now the question might ask, like, what is that in PSI? And then we'd have to convert from atmospheres to PSI. How about the volume? 8.5 liters. Moles. 0.55 moles. And the temperature, 306 Kelvin. 273.15, yeah. But we're already in Kelvin. And now we can just plug these things in. So pressure is the one we don't know. Volume, 8.5 liters, 0.55 moles. R is so it's multiplying 0.0821 atmosphere liter per mole Kelvin. And then times 306 Kelvin. So on the right side, we can take all those numbers and multiply them together. So 0.55 times 0.0821 times 306. So that's going to be I need to take my calculator off of scientific mode. That is 13.82. And what are the units going to be after that multiplication? ATM, yeah, atmospheres, liters, because we still on this side have 8.5 liters times pressure. So we can divide both sides there by the 8.5. Pressure is 1.6, only 2 sig figs. 1.26 atmospheres. All right. Moving on. So, again, another ideal gas law problem. But now we're given, right? Or now we're asked, how much volume does 0.556 moles of gas occupy when its pressure is 715 millimeters of mercury and its temperature is 58 degrees C? So this is exactly why. You should always write down R first. 821 ATM liters per mole Kelvin. Alrighty. So we are going to be using PV equals nRT. So our pressure, what's the pressure? 715, but it's in millimeters of mercury. So how do we convert from 715 millimeters of mercury to atmospheres? Because everything needs to be in atmospheres. That's how to convert it?
Well, first it wants you to convert inches of mercury to millimeters of mercury. So I did that, and then the next question says convert millimeters of mercury to atmospheres, and then it wants you to go from atmospheres to torr, and torr to like Pascal.
Yeah. Yeah. So what's this conversion factor?
760.
So for 1 atmosphere, it's going to be 760 millimeters of mercury, which is the same as torr. So millimeters of mercury and torr are the same thing. They're very, 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 very slightly different. So 715 divided by 760, 0.94. Say 08. And then our volume is what we're looking for. And what will the units of volume be? Yes, liters. L is for liters. And then N, what is N? Because I think this is the one that's, yeah. N is the moles. So like pressure, volume, temperature, those all start with the same letter, but N is moles. This is going to be 0.556 moles. And then the temperature, 331.15. Excellent. So I have atmospheres, moles, and Kelvin, so we can plug those in and say 0.9408 atmospheres times the volume equals 0.556 moles times 0.0821, and that's atmosphere liter per mole Kelvin. Always running out of space. And that's going to be 331.15 Kelvin. So 0.556 times 0.0821 times 331.15, and then divided by 0.9408. So the volume is going to be 16.1 liters. Okay. No questions? Everybody's good? All right. So now we're going to tie a couple of concepts together. And actually, this is the lab that we're going to do next week. So you're going to determine the molar mass of an unknown liquid. And you're going to do that by using the properties of that liquid as a gas. It's a pretty cool lab. You take Erlenmeyer flask, you put a little bit of foil on top, you poke a hole in it, and then you put a little bit of liquid into the flask, the unknown liquid. You heat it up so that all of that liquid becomes a gas, but some of it escapes through the hole in the top. But sort of once that's stopped, you can stop the reaction or stop the heat and let it cool, and then get the mass of the liquid that's still in the flask. And then the pressure of the gas is whatever atmospheric pressure is. The temperature will be, I think it ends up being whatever the temperature in the room is. I'll have to double check that one for the lab. Because I don't think Andy had thermometers out. But then you can take the pressure, the mass, and the temperature, and then the volume of the flask itself, and calculate how many moles of gas were in the flask. And then use the moles with the mass and calculate the molar mass. So you can use the ideal gas law to do that. So if you have a sample of gas and it has a mass of 38.8 milligrams, and its final volume, or its volume is 224 milliliters at a temperature of 55 degrees C and a pressure of 886 torr, find the molar mass of the gas. So key concept here being that molar mass is the grams per mole of a substance. Oh, that's taking a long time to update over there. Okay, it did get there eventually. So it's the grams per mole of a substance. And because we have, not the mass, because we have the volume, temperature, and pressure, which all go into PV equals nRT, we can plug those numbers in and find out what the moles of gas is. So pressure, volume, temperature, and then R is always 0.0821. So our pressure is 886 torr. We're going to have to convert that by dividing by 760. So that's 1.17 atmospheres. The volume, 224 milliliters, needs to be converted into liters. So 1 liter is 1,000 milliliters. So it's 0.224 liters. And the temperature is just going to be 55 plus 273.15. So plug everything in and solve for moles. N times 328. So 1.17 times 0.224 divided by 0.0821, oops, divided by 328.15. So 0.00973 moles of gas. There's one last thing we have to do before we can actually calculate the molar mass. Because what do we need to calculate molar mass? Grams. And what do we have for mass? Milligrams. So you have to convert milligrams. Convert milligrams to grams. So 38.8 milligrams. And how many milligrams are in a kilogram? So how many milliliters are there in a liter? 1,000. A millennium is 1,000 years. So if there's 1,000 milliliters in a liter, and we have milligrams, how many milligrams are in a gram? 1,000. Same conversion. 1,000 milligrams. Oh. That works. I would probably know it if you played it for me. 0.0388 grams. So we take our 0.0388 grams, divide it by the number of moles, 0.00973. And it's 3.99 grams per mole. Let me move that. It's 3.99 grams per mole. So one of the cool things here is you can't always do this, but sometimes you can use the molar mass to figure out what the gas is. Yeah, so if you look at the molar masses of the elements, that's kind of as simple as it gets. Helium has a molar mass of 4. So helium is one possibility for what this gas could be. This is the same molar mass.
What about why not hydrogen? Because that number is closer. Oh, okay. Sorry, I didn't see the 4.
Oh, yeah.
I was looking at the 0.00.
Oh, yeah.
And I was like, why would it be 1?
Because this would be the answer that we got. Yeah. So it doesn't mean that it is absolutely helium, but it's a close possibility. So in next week's lab, you'll have to calculate the molar mass of the gas, and then there's unknowns, and so you'll try to pick out of, I'll tell you what the possible unknowns are, or at least some of them, or give you a bunch of things, and it'll say it's one of these, and so you match the molar mass that you calculate to one of those possibilities. So we could run another one of these quickly through. So we're going to use PV equals nRT. So pressure, volume, number of moles, temperature, and then R is always 0.0821 atmospheres, liters per mole, Kelvin. And again, make sure you're always checking that your units match R. If your units don't match R, you're going to get the wrong answer. So here we have pressure, but the pressure's in 976 millimeters of mercury. So you have to divide by 760.
Why didn't we have to do that last time?
We did do that last time.
Well, I mean, no.
Oh, I didn't write it down.
Yes, sure. This morning we did it.
I didn't write it here, but I converted it to atmospheres. So if you take that 886 and divide it by 760.
What is 760 again? Over what?
So this is
1 torr equals 760?
yeah. So it's the same as saying multiply by the 1 atmosphere over 760 millimeters of mercury. So if you multiply across the top and then divide by the bottom, you end up dividing by 760.
The test, are you going to give us that? Like, do we have to memorize that?
Uh,
That formula and the R and the...
I expect you to memorize that 1 atmosphere equals 760 millimeters of mercury equals 760 torr. So I do expect you to memorize those ones. And the conversion to Kelvin.
And the R.
And the R. Yes.
What is R again?
It's the 0.0812 with all the
I know, but what does it stand for again?
It's the ideal gas law constant. So R is just a constant. It represents the relationship between all 4 of those variables: atmospheres, liters, moles, and Kelvin. So volume then is already in liters. N is what we're looking for. Temperature is going to be 88 plus 273.15. Because we need that in Kelvin. And then we can plug in all of these. And then solve for N. And then we have to convert from 827 milligrams to grams. So 827 divided by 1,000, 0.827 grams. And molar mass is what units? grams per mole. So the units tell you how to get the molar mass. If you have grams of something and you have the moles of something, you just take the grams and divide by the moles. So 0.827 grams divided by 0.01166 moles (70.9 grams per mole.
So for where you have it written out with the 1.28 atmosphere times the volume,
Yeah.
which side, so you multiply the left side and then you multiply the right side?
Yeah,
Or
so
do you
multiply these
just-
two, multiply those two.
Yeah, and then which one do you divide by?
So we want to get n by itself.
Okay, so you divide both sides by whatever side you're looking for is on?
Mm-hmm.
Okay.
Yeah, yeah. So remember, ideal gas law is the link between pressure, volume, and temperature of a gas and moles. If you have those three things, you can find the number of moles. And then you can do things if you also have the mass, calculate the molar mass. It's also a relationship that we'll use in doing more stoichiometry, of course. So this is sort of a bit of a footnote to talk about. So all the calculations we've been doing are for ideal gases. And that's actually a fairly narrow set of conditions. Real gases, especially at fringe conditions, they do have some small attractions between each other. So things like low temperatures and high pressures. So if there's a lot of gas particles and they're at a low temperature, then the attraction between gas particles does come into play. Now, we're assuming for all of our stuff, ideal conditions only. So you don't have to worry about that. If you take Chem 1, we'll talk about how those actually affect ideal gas law calculations, and there's specific little adjustments that you make. But these are just for ideal gases. So to change gears a little bit, according to kinetic molecular theory, each of the components in a gas mixture acts independently of the others. So it doesn't matter what the gas particles are. You'll notice, we've never talked about, and like N is the number of moles. It doesn't matter what type of gas it is. It still behaves under the right conditions as an ideal gas. And the calculations are all the same. However, sometimes we do care about what the components are. So the pressure of an overall gas is partially due to each component in the gas mixture. And so we call that the partial pressure. So if we have a gas mixture that's made up, like the atmosphere, of nitrogen and oxygen, mostly nitrogen, oxygen, and carbon dioxide, then the air is 70% nitrogen. So 70% of the pressure comes from nitrogen. And it's something like 20 or 30% oxygen. So 30% of the pressure comes from oxygen particles in the air. And this kind of goes back to the simulation. So let me swap screens. So in the simulation now I've added two different types of gas particles. Now there's the blue ones are the heavy ones, the orange, reddish ones are lighter ones. But if I remove heavy particles, so take note the pressure, let me change one of these things. So pressure is 11.7 atmospheres. If I remove, magically, all of the heavy particles, it should cut the pressure in half. Maybe I can add there we go. Let's get it to, nope, I guess it can't be 5. 5 would have been nice. But if I add in new particles, heavy particles, it doubles the pressure. But it doesn't matter what type of particles there are. So I could remove these heavy particles now. We go back to, this is a little bit weird, but adding in another 50 light particles gets us up to 11.2. If I take those out, we drop back down to, oh, the temperature's changing. So heavy particles, you get 13. Remove the heavy particles, 6.6. Add these, we go back up to 13. Doesn't matter what type of particles they are, but if we have different types of particles, the percentage of those determines the percentage of the pressure that particle makes up. Because now half of the collisions that are happening are from one type of particle. The other half of the collisions that are happening are because of the other type of particle. So we call that partial pressure. So for partial pressure of any component is the component's fractional composition. So how many, what fraction of the particles are what type. So like the partial pressure of, in that example, partial pressure of like the heavy particles would be equal to 1/2 times whatever the total pressure is. So I think when we had them in there, it was like 13.1 atmospheres. Or 1/2 is also the same as 0.5, which if you take 0.5 and multiply it by 100, that's 50%. So there's a relationship between the fractional composition and the percent composition. So air in our atmosphere is a mixture of 78, oh, I was wrong about that fractions, more nitrogen, 78% nitrogen, 21% oxygen, 0.9% argon, 0.04% carbon dioxide, and then a few other gases. So 78% of the total pressure in the atmosphere is from nitrogen. 21% is from oxygen. And it's independent of the other gases.
We're breathing all that in?
Uh-huh. Yeah, including the dust. So you've heard that optimists see the glasses half full, pessimists see the glasses half empty. That as a chemist, the glass is always completely full. It's just half full of water. Then the rest is nitrogen, oxygen, argon, carbon dioxide. Oh, come on. There it is. I don't know why this is being so slow. But so half full, half empty, or completely full. The glass, yeah. All right, so the fractional composition, then you take the percent composition and divide it by 100. So you get a proportion. So for this gas mixture of 80% helium, so we could take the total pressure inside of this, and well, actually, I don't have to do the math, but, all right, so the total pressure, P, TOT, is 1 atmosphere. And since this box contains 80% helium, that is the fraction of the pressure that comes from helium, 0.8 atmospheres. So pressure of nitrogen, since there's 20% nitrogen, is going to be 0.2 atmospheres. So to calculate that, or you get the fractional composition, you take the 80% divided by 100, and that would be 0.8 for nitrogen. Then we could say the pressure of nitrogen is equal to 0.8 times the total pressure. So we could plug in for that. That's 0.8 times 1.0 atmospheres means that the pressure of nitrogen is going to be 0.8. So it's fractional composition. So if we have a gas mixture that contains 64% methane and 36% ethane, if the total pressure is 1.44 atmospheres,
Why is it so slow?
I have no idea. It's probably the internet, because it's connected to my laptop over the internet. Trying to think if there's a way I might be able to connect it directly. Might as well just try it. This will still record everything. It'll just have that lag. But this way there won't be a lag up here. All right, well, apparently I can't connect it directly. All right, well. All right, well, we'll just have to deal with the delays. So we've got a mixture with 64% methane, 36% ethane. If the total pressure is 1.44 atmospheres, what are the partial pressures of each component?
So first you need to convert the percentages into a decimal, right?
So take that 64% methane, divide it by 100. That's 0.64 fractional composition of methane. And then we could take the pressure of methane would be 0.64 times the total pressure.
So you would multiply that by 1.44.
And then that's in atmospheres. So this fractional composition is always unitless. We just have to know that that is for methane. So the partial pressure of methane would be 0.64 times 1.44. So partial pressure of methane is 0.9216 atmospheres. And then you could do the same thing for ethane. This is 36% ethane. So that's going to be 0.36. You know, I mean, if you understand that, like, dividing it, you're moving the decimal place over, so you're going to get something like 0.36. You don't have to write out the dividing by 100, but you do need to convert it.
If this question was on like an exam, you would have to use the correct number of sig figs, right? So it would be 0.92.
Yeah, 0.92. And then, so we're just doing the same thing over here. So partial pressure of ethane is 0.52. And then those two together, because we only have the two gases, so if we added those partial pressures together, that should give us 100% of the pressure. So 0.92 plus 0.52 does indeed give us, so let me do this, 0.92 plus 0.52 equals 1.44.
It might just be easier to be like 64 plus 36 equals 100, so that would make up 100% of the total pressure, which would be 1.44.
You could do it that way, yeah. I mean, yeah, so then you don't calculate the individual partial pressures. If you have just two things in the mixture, then you could say, calculate one of these and then just subtract the partial pressure of that from the total, right? Because that would tell you what the other portion is. And that is actually leading into the next slide. which is Dalton's law of partial pressures. So the total pressure of a gas is the sum, or is adding up, all of the individual pressures of the gases. So for however many components there are, you can add up all their partial pressures and get the total pressure. And that would be taking our, like this, the 0.92 atm of, was that methane? Plus the 0.52 atm of ethane equals 1.44 atmospheres. All right, so equals that total. This chapter's long. So if we have a sample of hydrogen gas mixed with water vapor, the mixture has a total pressure of 745 torr. The water vapor has a pressure of 24 torr. So what is the partial pressure of hydrogen? So if the total pressure is the sum of all the other pressures, so the pressure of hydrogen plus the pressure of H2O, so we could plug in 745 torr for the total pressure. Pressure of H2 is what we need to know, and 24 torr is the pressure of water.
We don't have to do that 760 thing?
For partial pressures, you do not. So the reason that we needed to be in atmospheres for ideal gas law is because we're using the constant R, and that R constant has units of atmospheres in it. So here, as long as everything's in the same units of pressure, we don't have to convert it to atmospheres. So this ends up being 721 torr. We just subtract 24 from both sides, and that'll give us the pressure of hydrogen. Because all of the gases together will make up the total pressure. So there's a somewhat interesting effect on the composition of air when you're diving. It's actually the partial pressure of the oxygen that matters the most. So the best for human lungs is 0.21 atmospheres of oxygen pressure. But that composition changes, or that pressure changes as you go deeper or into higher pressures without changing the composition. So as you start to reduce the partial pressure of oxygen, well, you can get severe hypoxia. And so this is what happens. Well, this happens when you go up to higher elevations. I'd have to work out the math. For deep sea diving, you can get oxygen toxicity. So if you're diving and the pressure, remember when you're diving underwater, you have to have a special regulator on the tank that detects the pressure around you and then changes the pressure coming out of the tank into your lungs. Because if those pressures are different, then you can't take a breath because there's more pressure on your lungs than is coming from the tank. What that also does though, so let's say you go down like 20 meters and now you have 3 atmospheres of pressure. And the fractional composition of your oxygen tank is 21% oxygen. So times that fractional composition is 0.21. So 3 times 0.21 means that there's 0.63 atmospheres of oxygen. So go back up here actually. This scale, so 0.5 is safe, 100% oxygen is fine, but if you start to get too high, you can get oxygen toxicity. So now the partial pressure of oxygen is up to 0.63 atmospheres, and at some depth you'll get over that 1.4 atmospheres. So your body can't handle that either. So the other thing that happens is you also increase the partial pressure of nitrogen. And that can cause the nitrogen to dissolve into your blood, which causes nitrogen narcosis, also known as, quite poetically, rapture of the deep. Feels similar to being tipsy. So they use actually specialized mixtures of gases. One of them is heliox, so they replace all of the nitrogen with helium. And that helium won't dissolve in your blood as much and causes nitrogen narcosis. And they also are able to change the combination of oxygen and helium on the fly so that you're keeping those oxygen levels where they should be. So if you have a diver breathing heliox with an oxygen composition of 5%, wants to adjust his total pressure so that the partial pressure of oxygen is 0.21 atmospheres, what must the total pressure be? So you can set this up and say that if we want if the total pressure total, is equal to the fractional composition of oxygen. So we have 5.0%, divide that by 100. That gives us 0.05 as a fractional composition of oxygen. So plug in 0.05 times the partial pressure of oxygen that we want. So that's going to be 0.21. I think I'm doing this right. 0.05 times 0.21. This does not feel right. Oh, I'm sorry, I got these backwards. That's why. So, sorry, let me write out this equation. The partial pressure of oxygen is equal to, this fancy X is fractional composition times P total. That's how we would calculate the partial pressure of oxygen. So if we want the fractional composition is 0.05%, and our partial pressure that we want is 0.21 atmospheres, oops. Then we divide both sides by 0.05. There we go, 0.21 divided by 0.05. So we need 4.2 atmospheres to equal the total pressure. So 4 times atmospheric pressure.
Do the tanks change by themselves as the diver goes down deeper?
Mm-hmm. If you go below, I think below 30 meters is like technical diving. And you have to have special equipment to do that because you have to start dealing with this. It's actually,
Jump off the airplane. How come they don't have any oxygen? It's pretty high.
they're going pretty high, but for skydiving, you're not going high enough. If you do go up high enough, well, there's the Red Bull guy who like went up in a balloon. And he was wearing like a spacesuit because he went to the absolute edge of the atmosphere and then dove from there, and he did have to have oxygen. And even David Blaine got up to 21,000 feet or something, holding onto balloons. And then they started bringing him down because he was starting to get hypoxic and didn't have enough oxygen.
Have you seen like those people that climb like Mount Everest?
Oh, yeah.
Have you heard of Stoichiometry?
No.
He climbed Mount Everest with no oxygen.
That's insane.
He did it, and he climbed like all those crazy. He did like I think there's like all those, like the 4 largest peaks. Like you have Everest, like K2, and then
Yeah.
in like 2 months.
Huh. I bet there's some crazy anomaly with his blood.
Yeah. he
Would not
did,
be
like, all
surprised.
these studies and stuff, but it's on Netflix. His name's Arjan. He's from like
Oh,
Nepal.
huh. I'll have to
It's
check that
really
out.
interesting.
So we're almost there on this chapter, then we got to do the next chapter. I know. So for collecting gases over water, this is what, well, there's a thing that you have to take note of. This isn't doing it now. It was earlier. So anytime you have water, right, it's slowly evaporating. That's why, like, if you spill water and you don't clean it up, eventually it'll dry out. The water is evaporating. So inside of any container, so like this water bottle, there's going to be a certain amount of water vapor that stays vaporized in this, it's called a headspace, right? So this space. And in a sealed container, it'll go up and then it'll level off, and it'll stay there depending on the temperature. So unfortunately, this is the lab that we had to skip, where you take zinc, dissolve it in hydrochloric acid, you create hydrogen gas, and then you put a tube, this is similar to the one we were doing, you put a tube up into an upside down beaker. Now this beaker starts full of water. And then as you generate hydrogen gas, it starts to replace more and more of that space with hydrogen. But there is some amount of water vapor in there. So going back to Dalton's law of partial pressures, so the pressure total is the sum of all the pressures. So partial pressure of hydrogen plus the partial pressure of, in this case, water also. So if you do an experiment like this and you're collecting a gas over water, you have to subtract out that vapor pressure, the pressure from water. It's also called the vapor pressure of water. And usually you use a table, or there are calculators to find out what that partial pressure is. So if we collect hydrogen over water with a total pressure of 758, so again, we're going to use this pressure total equals the pressure of hydrogen plus the pressure of H2O. So our pressure total here is 758 millimeters of mercury. And that's going to equal the partial pressure of our hydrogen, which is what we want to know, plus whatever it is for water. So fortunately here we have at 25 degrees C, it's going to be 23.8 millimeters of mercury. So we can plug that in, 23.8 millimeters of mercury. And then you just subtract that 23.8 from both sides. So the partial pressure of hydrogen, 734.2 millimeters of mercury. So a lot of this stuff comes down to the fact that you've got all these particles mixed together. The total pressure is the sum of all of those. And then the last thing here. So we can also use gases in stoichiometry. Actually, I should write this up here. So, talked about, I can write it on the slide too, right? So we've covered this, grams of A, moles of A, convert from moles of B, convert to grams of B. Well, with PV equals nRT, say, just call this in here, PV equals nRT. Now if we have the pressure, the volume, and the temperature, we can take that and calculate how many moles of a gas there are. Like this is put. And then on the other side of this, we take this PV equals nRT, and then we can calculate from the moles of B, and we need some of these variables, we can calculate the pressure, volume, or temperature. I should call this A. call this of A, pressure, volume, or temperature of B. So now we've got a fork in the road. And we don't have to start with this and end with this. We could start with the pressure, volume, and temperature of A, calculate moles, and then calculate the grams of B. Or we could start with the grams of A, calculate the moles of A, moles of B, and then the pressure, volume, and temperature of B. So we're really just taking now all of this gas law stuff that we've covered, mostly PV equals nRT, and we're adding pieces to stoichiometry. So, right. Gases and chemical reactions. So in this reaction, we have 4.58 liters of oxygen. It's formed at 745 millimeters of mercury and 308 Kelvin. How many grams of silver oxide decomposed? So we're starting with our A here is going to be, right, we have pressure, volume, and temperature of oxygen. So pressure, volume, or volume, pressure, and temperature. So you say our P, V, N, T. So pressure is going to be 745 millimeters of mercury. V is 4.58 liters, O2, and N is what we're looking for. R is 0.02821 atmosphere liters per mole Kelvin. Temperature is 308 Kelvin. So only one unit that we need to convert. 745 millimeters of mercury times 1 atmosphere over 760. Millimeters of mercury, that is 0.980 atmospheres. So 0.980 atmospheres times 4.58 liters equals a number of moles, N, times 0.0821 atmosphere liter per mole Kelvin times 308 Kelvin. So .1775 moles of oxygen equals N. And then once we have the moles of N, let's start the stoichiometry problem. Sorry, moles of oxygen is what I meant to say. So no, it's a lot there, but that was all this piece, right? Just calculating, converting the things that we needed to convert, plugging it into PV equals nRT, finding N, or moles of A. So what's the next step? So it's the ratio between oxygen and what we're looking for, silver oxide. Yeah.
So we go 2 off of 2.
What's the coefficient? 1. So 1 mole of oxygen, 2 moles of silver oxide. And then we need the molar mass of silver oxide. Which I will trust that you can calculate. All right, it's 231. It's 231.735 grams over 1 mole. So then we take our moles of oxygen, multiply by 2, multiply 231.735. We get 82.3 grams of silver oxide. Yeah.
In the new stoichiometry quiz, is it going to be like the PV, NRT, and then the stoichiometry session?
Next week.
Next week.
Next week's quiz will be that. This week is just limiting reactant. So it's still grams to grams, limiting reactant. And I did post that one. Okay, so again, the only new thing that we've added is this, PV equals nRT. The rest of it is still stoichiometry, works the same way, canceling out units to get the final units that we're looking for, using coefficients from balanced chemical equations. So I swear, this is the last thing. The third last thing in this chapter is standard temperature and pressure. So it's what it is in the name. It is the standard temperature and the standard pressure. And those are just set values. So if you see STP, it's not a car auto part company, although it is also that. STP here in chemistry is standard temperature and pressure. So this is 0 degrees C, that's the standard temperature. The standard pressure is 1 atmosphere. Always. So we can calculate the volume of 1 mole of gas at STP. So using PV equals nRT. So standard pressure is 1 atmosphere. Volume is what we're going to calculate now. We have 1 mole of gas times R, which is still 0.0821. That's still an atmosphere liter per mole Kelvin. And then standard temperature is 273 Kelvin. I was debating on whether or not, because it's 273.15. That's what I use. But
I would just add the 1.15 because that's pretty thin.
that's what we've been doing.
Yeah, and it's kind of like
Yeah.
makes it more complicated.
I would accept either in that case. So, yeah, 273.15, that's our standard.
Kelvin, don't forget that.
Yes. Kelvin. So now, technically, we'll divide this 1 atmosphere on both sides. So divide both sides by 1 atmosphere. And technically, we'll multiply by 1 mole. But because they're 1, we don't need to actually type that into the calculator. We can just do 0.0821 times 273.15. And that's going to give us 22.4 liters. So, and this is a shortcut idea here. At STP, so when it's standard temperature, 273.15 Kelvin, and when it's 1 atmosphere, 1 mole of any gas will have a volume of 22.4 liters. So this is the molar volume of a gas. ideal gas at STP. So molar mass of any chemical, right, is grams per mole. This is similar things that we do it upside down as liters per mole. Actually, it's not upside down. Yeah, it's fine. It's liters per mole. So 22.4 liters per mole, just like for any other compounds, right, you can calculate grams per mole. That's molar mass. This is molar volume. But it only applies at STP. Yeah, very convenient conversion factor. Look for this on exams because I like to throw in things that are like, you know, you could solve it. You don't need to use the shortcut, but here's a problem where you could use a shortcut if you remember it. If you don't remember it, you'll still be fine. But remember that 22.4. So for any gas, doesn't matter what the mass of the gas is, the molar mass, it's still going to be 22.4 liters. So how many liters of oxygen at STP are required to form 10.5 grams of water? So we could say, right, we're starting with grams of A. And this is where pretty much no matter how the question is worded, it will give you an actual solid quantity of one of the things. It's either going to be grams or it'll give you like pressure, volume, and temperature. Usually volume is the thing that determines the amount. But we have grams of water. So that's where we're going to start. 10.5 grams H2O. I'm just going to fill this one in. That's 18.02 grams of H2O per 1 mole H2O. What's the molar ratio?
2, no, 1. 1 mole of H2, on the top is 2. Wait, on the bottom,
What's the coefficient for, or what,
1.
for oxygen? So we want to find oxygen. So that's what,
So 1 mole of oxygen,
1 mole of O2. And then what's the coefficient for water?
H2O, 2, there's 2.
Yeah, so it's this one, the 2. There it is. So 2 moles of H2O. And then,
We keep going, huh?
yep. But now, this is where we're at STP. So because we're at STP, we can use 22.4 liters per mole. So for 1 mole of O2, we'll have 22.4 liters of O2. So now we don't have to do PV equals nRT. And we get a conversion that we can plug straight into the stoichiometry grid. So 10.5 times 22.4 divided by 18.02 divided by 2. And it's 6.53 liters, sorry, not grams, liters of H2O. Yeah. Yes. Sorry. Oxygen. Are there any other questions?